we have this system over here. We have this kind of duality between a block with a time domain signal going into a block and a time domain signal coming out, and the kind of stuff that we've been doing math with, right, where we have the Laplace transform of the input signal, the Laplace transform of the system, and the Laplace transform of the output signal. So the misperception that many people have is that this multiplication may perhaps correspond with multiplication in the time domain as well. And I'm not going to use the word obviously, but that is obviously not correct. So multiplication of two functions of S, if I were to invert that Laplace transform, I would actually end up over here. In other words, I would be convolving signals with one another. And we've spent quite a lot of time speaking about how fundamental the exponential function is when studying differential equations. The exponential function happens to be what is known as an eigenfunction. It's related, that eigen, if it sounds familiar, it's related to much the same kind of idea as an eigenvector. But the basic idea is that the exponential function is the only function that is unchanged by differentiation. Right? That's why everybody loves working out the derivative of exponential functions. Super easy, right? Now, that exponential function, it's important to understand how that works when you understand differential equations because it's got that fundamental nature, right? It's the thing that builds up the base of all of the solutions of differential equations. But, similarly, it is very important to understand that there is this convolution relationship between the inputs and outputs of a differential equation or a system described by differential equations that can be captured by this slightly weird idea that I will take not the Laplace transform of the system, and I'm saying weird because it should feel a little weird by now because you're used to just multiplying by the transfer function. But I can actually work out the inverse Laplace transform of g of s. Right? That's perfectly a possible thing that I can do. And, in fact, I have a special name for it. I call it the impulse response. And so g of t, small g of t, is really the inverse Laplace transform of big G of s. And this is an important idea to hold in your head, that we can do inverse Laplaces on the equations describing the system just as well as we could do inverse Laplace transforms on equations describing a signal. And it's a lot easier to imagine that u of t is actually a function of time than it is to imagine that the system is in some way related to a function of time. But actually, that's what the mathematics tell us. So this, I admit very fully that this is perhaps a slightly counterintuitive idea. But if we work the math this way, this is really what you've been doing every single time when you've been taking a Laplace transform of a system, sticking it into SymPy, right? Taking a Laplace transform of an input, multiplying the two, and then inverting the Laplace transform. You've just been using Laplace transforms to calculate convolutions. Right? Because every time you multiply in the Laplace transform, in the Laplace domain, you are convolving signals in the time domain. Multiplication in the Laplace domain corresponds to convolution in the time domain. That's what it means, or that is how that multiplication came about. Now, if you search in your heart, you will find I have never motivated that equation. I've just written it down, and you've just believed it. That's basically how the textbook handles it, right? It just says, look, we draw this block diagram, and look at this. Like when I do this, when I draw this diagram, hey, presto, it's magic. You just multiply these, and it just works. And then I've spent a lot of time showing you that it works. But the actual mathematics behind that, if you were doing this in calculus, you would actually be calculating the convolution. And it has to do with this idea that you can calculate the output of a differential equation or the solution to a differential equation that is specified in time by calculating this convolution only in time. So notice that here we're going on a bit of a tour, a side tour through the Laplace domain, which by now feels very natural, hopefully. But what the math tells us is that if we look up the definition of the convolution on Wikipedia, and we copy and paste it into this document, and we kind of apply that integral, we will get the same numeric result. So we can calculate outputs from differential equations without ever touching the Laplace domain, by just knowing the impulse response of the differential equations. Now again, it is in principle possible for me to calculate g of t without using the Laplace transform. So I can calculate g of t without using the Laplace transform. I can calculate all of this stuff without using the Laplace transform. All of that stuff is something that is possible to do. I do not recommend that you actually do it except for two specific reasons. The first reason is I feel that the convolution form gives you great insight into the behavior of transfer functions that allows you to predict what they're going to do without doing any math. In much the same way that understanding the roots of the denominator have an effect on that output has. And as soon as you start understanding how the convolution works, and I'm going to show you a couple of animations that hopefully kind of solidify how this works. So I feel that form yields a great deal of understanding if you understand that this is true, that the convolution works the way that it does, and if you can visualize the convolution integral happening in your head, and you can visualize an input being pushed through the impulse response in the way that I'm going to show you now, that gives you a great deal of deep insight into how this is actually working. The second reason why you may want to do this is if you want to calculate the effect of an arbitrary input on some system that you cannot 100% accurately describe using differential equations. And in that case, we're going to use the discrete convolution. We're going to talk more about that a little bit later. I have a notebook where we do effectively convolution transforms on like an MP3, right? And that's a very good application of that idea. But today, I just want to focus on ways in which we can build intuition about how general systems will behave. So by now you know how first and second order systems behave. How could we kind of map that onto general systems? So once we know that the convolution works this way, that multiplication in the Laplace domain corresponds with convolution, we suddenly find ourselves wanting to calculate convolutions, and unfortunately SymPy kind of leaves us in the lurch there. I suppose by now, if you are familiar enough with SymPy that this is something that you could picture doing, you could actually say, well, I can take that integral. That's just an integral, right? So I can just plug that into SymPy, and SymPy will do the integral for us. Unfortunately, not so much. So in the current version of SymPy, and let me just actually execute this. So in the current version of SymPy, that does not in fact work. So I try to evaluate that integral, and I know that this integral, which is the convolution integral, should be giving me this same result, right? Because if everything that Carl just said is true, that convolution integral corresponds with that step response. But it doesn't work that way. And so we are forced to use numeric methods. And there's a bit of a diversion here in the sense that I now want to calculate the convolution integral numerically. And I find myself reaching for a tool that will allow me to avoid kind of getting into the weeds of actually doing the convolution integral. You know, it's complicated, right? Like there's the tau is moving in one direction and the t is moving in the other direction. Maybe I don't want to get myself caught up in those loops. And I type numpy and con, or maybe I remember yesterday's lecture where Carl said, hey, there's this thing called convolution, which is effectively like multiplying polynomial coefficients. And it turns out, yes, that numpy has this function called numpy.convolve. And what numpy.convolve does is it calculates discrete convolutions. That's what it does. Now, unfortunately, discrete convolutions are related to continuous convolutions, but they're not exactly the same. So that's the formula for the discrete convolution. And I've added in some steps here. You can compare that now with the definition that I had earlier of the continuous convolution. And you'll see that they are very similar in the kind of way that discrete and continuous things tend to be. So there's a sum instead of an integral, and the limits are roughly the same. And instead of continuous t, I have discrete elements m and n. So there's a little bit of mathematical sleight of hand here where I expect you to know that obviously m and n are integers, and obviously t and tau are real numbers that can take any number. But basically they are, you can see, very much the same. So I can use the discrete convolution to approximate the continuous convolution as long as I understand that I'm going to be out by a factor of some kind of a discretization time. Right, so what I've done here is I've just written out the Riemann sum for this continuous integral. Right, so I've just said, okay, I can take this continuous integral, I can use a Riemann sum to map that out. So Riemann sums are those blocks, right? So I'm just approximating the integral by the sum of a lot of like rectangles, right? And those rectangles are g of m delta t high, and they are they are that high and they are that wide, delta t wide. Okay, and so you can see a little bit of manipulation allows me to see that there's a discrete convolution hiding in there, but it's been but in the approximation I have to multiply by delta t. But effectively I can use the discrete convolution to calculate the convolution for me. I don't have to get involved. Now that's a lot of build-up, but the actual application is super easy, right? I evaluate the two functions at different times, and I plug it into the convolution function, and I get this result, which is not at all what you expect. It's kind of what you expect, but it's bigger, right? If only all things work that way. The reason why this is doing the way that it is that it is actually, remember that the discrete convolution is theoretically an infinite. It's doing that sum from negative infinity all the way to positive infinity. And so to capture all of the possible terms, all of the terms where there's any kind of chance of overlap of the functions, it's calculating with pads. It's kind of making the out parts 0 and then calculating with pads these integrals. But the part that we are really interested in is just that first part. And so we can easily just index that out. And so this actually allows us to, this is now a whole new way of calculating the output of a first order system to an arbitrary input signal. I've used for now just a step signal, but I do not have to change this code one bit to use a u of t that is different at every single time period. Right? I just plug it into that convolve function, it convolves it with that, it is also known as a kernel, but what we'll be calling an impulse response function, and out pops the answer. So that's very convenient. Now, the next thing I want you to understand is that you would be able to kind of predict what that looks like if you took apart the convolution integral. So I've built here a little GeoGebra sheet which allows us to explore the convolution integral. Now, basically what we have is this red line is u of t, right? So that's a unit step that goes up to there. So you can see here we've got that we've got the input signal going over there. That's u of t, and then we've got this kernel, which is the impulse response. And notice that it's going with its time in the opposite direction. It's maybe a little bit hard to see, but look at the integral, right? This integral is d tau. So the integral is running over tau, while this variable is a free variable in the integral. So that's in the same way that the Laplace transform, I integrate over time, and then I don't have time left anymore, and I end up with only s, right? In the convolution integral, I integrate over tau, and I don't have any taus left by the time I've done that integral. I just end up with a function of time again, right? Coming in now, there you go. That g over there is that shifted and inverted version. Let me just move this a little bit so you can see. Okay, so you can see I'm moving tau around, and what moving tau around does is it basically moves that shifted image around. So as tau moves forward, that function moves forward. And so look at what is happening, right? I'm taking that signal and I'm pushing it through, and what I'm drawing on the blue line is the product of u and g. And so you can see the product is 0. And also remember that this exponential function that we're working with is this special modified exponential that we get when we invert the Laplace transform. In other words, it's an exponential function that is 0 for times less than 0, and then only starts at 1 and goes down, right? And so this g is actually going, it's kind of a little bit hard to see, but there's actually, g goes all the way to there. And so the product, when tau is negative, is 0. 0 across the whole line, and this little c over here, let me just show you how that's defined. That's defined as the integral of the product. As those two start overlapping, I want you to have a look at what the integral is doing. So the integral is this brown region, right? So does everybody see the moment, so I've got a 0, the blue line is flat, right? The blue line is flat, the blue line is the product term. So the integral of 0 is 0. No surprise. But as soon as tau hits a little bit positive, right? Up to tau equals 0, there's no integral. As soon as tau becomes a little bit positive, I start getting a little bit of area, right? And actually, if you think about what so that's, remember, that's the result. That's the resultant integral, right? So that function, notice how as I sweep this out, I actually sweep out that integral. And for every point, I get, as that moves in, I get more integral. Up until the point where I start getting the full, up until this point where I start getting kind of diminishing returns, right? Now, moving more of that function into that space isn't contributing to a greater integral. Right, so does everybody understand what's happening here, right? This is the convolution in motion, where I've got, that's my u, here's my shifted g, right? My shifted and reversed g. I'm moving g across that time, and I'm calculating that integral. And as I move this across, I end up with a bigger and a bigger integral. I can spot y. If you look closely, you can spot a large number of the characteristics of that step response by imagining that curve hitting, or those two curves hitting one another, right? It hits with the big part first. And that kind of is correlated with this idea that the slope of that step response is large at the beginning, right? And as it keeps going, less and less surface is produced, which corresponds with this kind of fading out idea. And now what this tells you is that if I could sketch an arbitrary curve, right, and you could do that and you can kind of simulate it in your head and say, right, there's a big part to at that point, so it's moving in, and that's going to make a great contribution to the integral initially. And as it moves through, it's going to become less and less. And so understanding how these convolution integrals work actually allow you to take an impulse response, look at the impulse response, and say, I know exactly from that impulse response what the step response will look like. I know exactly from that impulse response what all the responses will look like, as long as I can do a convolution in my head, as long as I can kind of picture a convolution in my head. Because all I need to do is to take whatever that input is and imagine the convolution of the impulse response with the target input signal. Does everybody see this? I'm gonna. There are already links to the first and second order GeoGebra notebooks on ClickUp. They're live on there, so you can click on them. I'll do the same here. But the thing that I'm wanting you to go for when you look at these convolutions is an intuitive understanding of, would I be able to sketch freehand the convolution if I were given sketches of two input functions? Now, I say specifically sketch because what I'm trying to get at is, if I removed the computer from the equation, if I asked you to use only your brain and no mathematical manipulation at all, I want you to move to a place where you can picture what that convolution integral will look like. So I'll post a couple of these resources, but this is really the key, right? That if you translate kind of one-to-one what's happening here, right? We've got this u of tau, we've got this g of t minus tau. Effectively, what that tau is doing is it's rotating and shifting. So I've got, at a particular time, I've got a rotated and shifted version of g of t, which you can kind of picture moving through. And the integral, the thing that I'm trying to get is the integral over that whole function, so which is this blue function product. So that's the product. So it's cutting out that part of that response and integrating. So that's basically how that is working. Right, so, but now you're saying, okay, this helps me not at all, because I still need a way of understanding what the impulse response looks like. And right now, the tools that I have to understand what the impulse response looks like is inverse Laplace. So if I'm inverse Laplacing anyway, I might as well just inverse Laplace all the way to the answer instead of inverse Laplacing and then getting this very tenuous connection to the impulse response and then picturing everything in my head. Now, what I'm hoping is that this will pair with the thing that I showed you yesterday, which I'm just going to build again quickly, which is this idea that if I take the Laplace domain, I can imagine the Laplace domain as being a parametrization of E, right? So I can say, if I choose some arbitrary S, I can always plot the real part of S times X and the imaginary part of E to the S. Now, I'm using X here just because that's what GeoGebra uses. And effectively, this is the family of functions that the Laplace plane maps out, right? So basically, what you're looking at here is the complex plane. And I'm choosing a point S, right? And that point S is related to this family of exponentials, right? Just to kind of, so that's the full family, right? And you can see that we can see some very interesting things. We can see that on the real line, there's no imaginary component, right? So we're working just with real numbers. If I move off the real line, I get these oscillating functions through the Euler relationship. As I move closer to the imaginary line, and on the imaginary line, I get exactly sinusoidal and cosinusoidal behavior, which is what I expect through the Euler relationship. And then when S has a positive real part, which we will be describing, and you'll see me abbreviate this a lot, we'll be describing that as the right-hand plane and the left-hand plane. And so you'll see lots of references in the textbook to left-hand plane poles and right-hand plane poles. And if you only know this, if you know that the impulse response, now notice this, right? When I put S over there, look at the real part of that exponential. That looks very much like the impulse response of a first order system. Not only does it look very much like it is it, right? And in fact, it is it in exactly this way, that as that S moves closer to the imaginary line, remember that the root that I'm looking at, if I'm working with a first order function which has a denominator tau S plus 1, is 1 over or minus 1 over tau. Right? And so large poles, or poles with large negative components, right, are associated with high taus. And we can see that immediately emerging as or low taus, I mean, because it's 1 over, right? So as I get smaller, 1 over tau gets bigger. As S gets smaller, 1 over tau gets bigger. As S gets bigger, 1 over tau gets smaller. And we can see that. So those big poles are associated with a fast response, and the small poles are associated with a big response. And so basically what I'm giving you here is a two-step process for imagining responses in your head, right? Going from a Laplace transform, you can imagine the impulse response by knowing the relationship between the poles and the impulse response of the transfer function that you're looking at. Which is just this, right? That the impulse response will be a linear combination of all of the prototypical S's at the poles. And so remember, we can't get one complex pole, we have to have two. And so that impulse response, there's only one of them, and they have to combine to produce a real output. So they'll be combining in a way so that the imaginary components go to 0 and the real components add together. And that basically explains everything that you need to know. If we look at our second order, for instance, just make a new window. So hopefully this will give you a new way of looking at this second order response chart now. I'm just going to close this so we've got space. So here we have the same idea we've got, but I've split the planes. So on the left we've got the complex plane, and on the right we've got time, right? So here the x-axis is time. Over here we've got the complex plane. And you can see very clearly that as I move zeta, let me just zoom out a bit. As I change zeta, I get slightly different kinds of responses. I'm going to make that faster as well. But I can move my S, and I can kind of say, what does e to the st look like there at that pole? Oh, look at that. It looks exactly like the impulse response of that second order system. Right? Does everybody see? That red line over here is the impulse response of the second order system, calculated just using the formulae in the book. Okay? It's just the inverse Laplace, effectively, of that second order system. I've calculated the roots of the denominator, and not by chance, but because this is how the Laplace transform works, if I look at e to the st, the associated e to the st, I can see that that is exactly what that response looks like. Now, a lot of you are hopefully saying, but wait a minute, Carl, that's the imaginary part of the response. It looks exactly like the imaginary part of the response. Remember, I said the actual response will be a linear combination of both of those two S's, right? So in other words, there's one over there, and there's one over there. And we'll combine them using coefficients that are chosen so that the final output is real. And those coefficients can be imagined. And so we'll just combine them in such a way so that we have only a real response. But I can tell you now, this is not a coincidence, the fact that the imaginary response effectively matches up exactly with the value of e to the st at that position is exactly by design. So this allows you to go in your head to say the S-plane is a parameterization. It tells me where my functions, every point on the S-plane is a single e to the st. Right? On the left, we have stable e to the st's. On the right, we have unstable. On the real plane, we have pure real responses. On the imaginary plane, we have sinusoidal and cosinusoidal responses. And effectively, you can say, right, there's a space, every point that I can point to on that plane corresponds to a particular exponential. And that's interesting because every solution to differential equations corresponds or is a linear combination of these kinds of functions. Right? So by understanding all the kinds of e to the s's that I can get, or e to the st's that I can get, I effectively understand all the shapes of the impulse responses of transfer functions. Right, so the first part of this is understanding these poles. Now, the poles are the easiest to explain because, as I mentioned yesterday, the Laplace integral goes to infinity when e to the st is equal to e to the minus st, or when that product is 1, right? So when the product is 1, I get an infinite integral. And so it's easy to explain why I would get these points of infinity at that point. Interpreting denominator dynamics is slightly harder. I'm not going to talk about it today because I'm focusing on insight. We're going to talk about the denominator stuff. It does get a little bit tricky a little bit later. I really want you to kind of just internalize this. From the fact that you can look at the S-plane and get an impulse response effectively just by looking at it, at least in character. And from the fact that you can then go further and use your insight about e to the st to picture it being convolved with the input that you have. If you practice a little, you can basically predict what the output will look like by just looking at the transfer function and not doing any of that inversion at all. Right? What's the root? You first figure out what the poles are. You think, what do the e's look like that are associated with those poles? And then you figure out what would it look like if I did the convolution integral? What would it look like if I pushed that through my input in this kind of reversed way? Would it have a lot of initial behavior? So for instance, this particular impulse response starts at a non-zero value. And that kind of tells you that it's going to grow very quickly. If it started at a 0 value, we would imagine that it would kind of take a bit of time before it picked up steam, just like we could imagine with a second order impulse response, right? So if the impulse response looked like this one, right, you could imagine why we're seeing the output behavior that we're seeing by imagining it through the impulse response, or by imagining it through the convolution integral. So I've got a couple of ways that you can think about it now so that you can kind of say, okay, this allows me to predict the behavior. I want to round out the lecture today by going a little bit further into the way that we visualize these things. We've already spoken about the poles and zeros, but I'm also going to spend a little bit of time visualizing complex functions by a technique which is known as domain coloring, because I feel that it gives a great insight into the behavior of transfer functions. Now, you can see what I've done over here is to get real functions of a complex number, right? But if I'm looking at a transfer function, I actually have a complex function of a complex number. And I've done this over here in the second order visualization. I've taken G, and as I move S around, now forget about the right-hand side over here. I'm actually going to turn that graphic off. I'm going to just move that open. And rather focus on what is called the image of G. In other words, this is G of S. It's the actual complex number that results if I plug this S into this G. right? And so you can see that actually for every s, there is a corresponding g of s. That's unsurprising. But I want you to understand that we have some challenges in the way that we can actually produce graphics that show this relationship. Because unlike before, where we had a two-dimensional plane and we had a one-dimensional function, now we actually have a two-dimensional s, it's got a real and an imaginary component, and we also have a two-dimensional g, which means we've plumb run out of dimensions right there, right? Because we only live in a three-dimensional world. And so there are some significant challenges in doing something like, so what's easier than doing this, right? Sine of x. Beautiful, super easy. Why? Because I've got a dimension for everything that I need, right? I've got a dimension that I can allocate to x, and I've got a whole other dimension which is perpendicular to it that I can allocate to y. So I can draw this plot that shows me every combination, every possible combination of x and sine of x. Unfortunately, I have no similar way in terms of actual dimensions. I have no similar way of plotting the relationship between s and g of s because I'm out of dimensions. Now, there are some clever ways around this. But the first thing I want you to look at is just the behavior of how these things behave. So you can see that if I choose a s, there's clearly a value for s, a real and an imaginary value, and there's clearly a real and an imaginary value for g of s. But I also want you to think about this geometrically. So in other words, we could also say that there's a line that connects that over there, and there's also an angle, right? So we can basically say there's an angle over here. That angle is the angle that g of s makes with the positive real axis. And so you guys have come across this kind of duality in complex numbers before. In many cases, it's useful to think about s as having a real and imaginary component, and it's kind of the easiest way to think about it if I'm just moving things around. But notice that as I move s around, I will see different angles and different lengths for g of s. Now, this insight we can use. So I've got a notebook on this which is earlier in the study theme, but we can actually use colors to represent at least one of the dimensions. And by convention, we use a very special way of doing this called domain coloring, where we use the color to represent the angle and the brightness to represent the magnitude. And what this allows us to do is to have a two-dimensional representation of g of s. So what we're seeing here is exactly that same second-order function that I was showing earlier. But now I can see for what values of s will g of s make the same angle with the real axis. So all of these yellow areas have the same angle, right? All of these blue areas have the same angle. And I can basically use that as an aid to visualization. This is a very useful way of getting an image of g of s. And we'll be reasoning through these angles and magnitudes a little bit later, but I want you to kind of be familiar with these because I'm going to also be showing some of these visualizations later.